If you've worked with Kubernetes, you know that for many, it can be quite a complex machine. Between all of the moving parts, the networking, and often just getting the cluster up and running properly, it can take time. And by properly, I mean secured, with secure communication, proper network isolation, secure secrets, etc. Unfortunately, getting the cluster up and running isn't enough. Kubernetes isn't safe by default. It needs further tweaking to ensure not only cluster safety at a high level, but pod and container safety as well. In the 2022 State of Kubernetes Security Report by Red Hat, where 300 DevOps engineers and security experts were polled, it was reported that respondents, quote, worry the most about exposures due to misconfigurations in their container in Kubernetes environments. That was 46%, nearly 3 times the level of concern over attacks, 16%, with vulnerabilities as the second leading cause of worry at 28%. Getting important configurations right, like role-based access control and security contexts, is vital to a cluster's security posture. There are factors that DevOps teams need to consider overall, as well as within the scope of their own unique situations. So while we obviously can't cover all configurations in this video, I want to present a few initial strategies that teams can make from the outset of the cluster deployment that will greatly increase their security posture. Let's take a look at these. Securing etcd is critical to Kubernetes security. All cluster data, including secrets, is kept in this highly available key value store. Gaining read or write access to etcd is basically obtaining admin access to the cluster. So you need to plan protection for this vital backend from the outset. And there are 3 things you can check when securing your etcd. Number 1, encrypt your data at rest. By default, etcd data is not encrypted. An encryption configuration object needs to be created for etcd data to be encrypted at rest. Here's how to do it. First, you need to create an encryption configuration object in a file and save it to the control plane node. You'll need to SSH into this node and create it in a separate folder there. In my example, I saved it to etc/kubernetes/enc. And be sure to set a secret here. This key will be used to encrypt your data. Next, head over to the Kubernetes manifests at etc/kubernetes/manifests, and you'll need to update your Kube API server manifest. First, add an encryption provider config flag and point it to the location of the encryption configuration file that you just created. In addition, add this file's location as a volume and mount it. Now, after restarting the API server, any newly created or updated etcd data will be encrypted at rest. And this includes your secrets. We can test it out by first creating a new secret, then reading that secret out of etcd using the etcd-ctl CLI. If you see the AES CBC encryption type here in the output, then you did it right. Congrats, your etcd data is encrypted at rest. However, there are a couple of problems here. Number 1, your encryption key is sitting there encoded, basically plain text, on your control plane node for the viewing. Second, you'll need to rotate this key at some point, and that's not a trivial task on a production cluster. And finally, even though the Kubernetes documentation walks through what we just did as its encryption at rest example, it also notes that this encryption type isn't safe. In fact, if we look at the encryption types, so we use this one here, AES CBC, it's labeled as weak and not recommended due to CBC's vulnerability to padding Oracle attacks. The type above it is also not recommended for use except when an automation key rotation scheme is implemented. It must be rotated every 200,000 writes. Above that, we have a strong encryption type, but it's a newer standard and may not be considered acceptable in environments that require high levels of review. So that leads us to the last in the list here, which is the strongest and the recommended choice. And this is using the KMS provider. Now with this KMS, or Key Management Service provider and plugin, you can essentially manage the encryption key outside of your cluster. And with third-party providers like AWS KMS, Google Cloud KMS, or HashiCorp Vault, adding the security and simplicity of key rotation for you, it's a no-brainer. There are also other alternatives like the External Secrets Operator or Bitnami's Sealed Secrets. But whatever route you go, the takeaway here is that you handle this encryption early on and that you encrypt your etcd data at rest. The second thing you can check when securing your etcd is that you're restricting access. It is recommended to separate the etcd server and isolate it behind a firewall. From there, only access from the API server should be allowed. No other components in the cluster should be allowed direct access to it. And the third thing to check is to ensure that the API server is using TLS. By default, Kubernetes allows all pod-to-pod traffic inbound and outbound. Maybe you have a small namespace where all pods need to communicate openly, but for most scenarios, this needs to be addressed. If attackers gain access to a pod, then they can move to other pods unhindered. To prevent this, network policies can be put into place to restrict unnecessary namespaced pod-to-pod access on the network or transport OSI layers. One big step you could take at the outset is just to set an all-out deny-all network policy to deny all pod-to-pod traffic in a namespace. And what's great is network policies are actually additive. So you can set a deny-all network policy and then add allows as needed. Now let's put this together in a classic example. Let's say we have a front-end application in a pod, another back-end pod, and then a database pod. The front end ideally should not be allowed to talk directly to the database, nor the database to the front end. Instead, the front end should only be allowed to talk to the back end, and in turn, the back end to the database. So if attackers compromise the front end application, they won't be able to touch the database directly without going through the back end, thus complicating the scope of penetration. So we can start with the default deny network policy, ceasing all traffic for that namespace. Then we can create a new network policy for the database pod only, to allow ingress from the backend pod only. Then we could add another to address the backend pod as well. So remember, Kubernetes by default allows all pod-to-pod traffic. Use network policies to restrict this at the network layer. If you need to expand and restrict access at the application layer, then you can look into a service mesh like Istio. In addition to open networks, pod-to-pod communication is unencrypted by default. This means anyone who is able to infiltrate the cluster can listen to communications in plain text. To secure this, you can use, again, a service mesh like Istio or Linkerd to easily enforce mutual TLS. And what I mean by easily is that they both enable mutual TLS by default between meshed pods. In the example of Istio, Istio deploys an Envoy proxy to each application container that will enforce TLS encryption within the service mesh. Now, be sure to change its configuration from permissive, which allows TLS and plaintext to be used, to strict to enforce TLS only. Next, let's talk about access to the cluster itself. Any user coming to the API server with a valid certificate is technically considered authenticated. Given this fact, there are a few suggestions here. First, in most cases, anonymous auth should be disabled by setting the anonymous auth flag to false for the API server. RBAC should be set up to handle specific users. However, if anonymous auth must be used, RBAC should greatly limit what anonymous users can do as a whole. Second, by default, the API server listens on two ports, one secure and the other an insecure localhost port. You should disable the insecure port by setting the insecure port flag to 0 and ensuring that the insecure bind address is not set. This insecure port will actually bypass authentication and authorization checks, something you do not want in place if someone malicious were to gain access to the master server. Next, a secure and well-maintained RBAC system should be set up and in place at all times. And finally, admins should consider managing normal user accounts with corporate solutions like Active Directory, Okta, etc. via OpenID Connect. An open source application like Teleport provides secure access to Kubernetes clusters by way of short-lived kubeconfig files and certificates via single sign-on. In addition, Teleport provides additional tools like a built-in RBAC system to control access and auditing of kubectl events, not only for your cluster, but for tens, hundreds, even thousands of clusters in one graphical user interface. Roles and policies can be put in place for users to access clusters easily and securely. In fact, users never directly access the clusters, which can sit isolated in a private network or behind a firewall. Direct interaction is only with Teleport's proxy service. You can download and get started with Teleport today at goteleport.com. Now, what about security at the app level? There are talented application developers who will take their apps, containerize them, and deploy them often without a good grasp of the inner workings or ideal settings of a Kubernetes cluster. Helm charts from public repos or public Docker images may contain root-level access or other potentially critical configurations that could weaken security. Therefore, it's important that YAML configurations and containers coming into the ecosystem be audited. Whether this is performed manually by a security team or through a more automated approach like vulnerability scanning, this can help catch potential loopholes before they come in. In addition, we should use the Kubernetes security context at the pod or container level to block any images running as root. We can add a security context entry into the YAML with run as non-root as true, and the kubelet will refuse to start any image that defaults to the root user. Of course, taking a step back, images should be assigned a user in a group UID, but adding this security context will add another layer of defense if not. There are other security context settings that can be of use to your situation, as seen in the documentation. In conclusion, if you're spinning up a new cluster or have done so recently, remember that it isn't overly safe by default. You'll need to put in some work to secure it further. By implementing these 5 strategies we've talked about in this video, you can greatly improve the security of your cluster and the success of your applications overall.